he's done some work with Bruce Strain, and is doing most of his thesis now with Jeremy Goodman, who, as many of you know, does many things in astrophysics sort of very carefully and carefully. So I was impressed when I was in Princeton in December, and Jeremy was telling me a little bit about this project and was, saying that, Eric is, very details oriented. So if Jeremy Goodman says you're details oriented, that means you're doing things pretty carefully. So we're looking forward to hearing what Eric has to tell us about tides in planets.
All right, thanks, Andrew. Well, I'll spare you many details today and hopefully just give you a snapshot that you can take away easily of some atmospheric physics occurring in the atmospheres of extrasolar planets. In particular, I'm interested in the role of gravity waves in controlling the atmospheric structure of these planets, which hasn't yet been appreciated. Now, when I say gravity waves, I'm not talking GR. These are purely hydrodynamic phenomena that are very familiar to terrestrial meteorologists. And what we've got here is an image taken from a satellite over the Indian Ocean. This is about 250 kilometers by 400 kilometers of a cloud deck at an altitude of about 2 kilometers above sea level. And what you see is the imprint of an atmospheric gravity wave on these clouds. So this wave is propagating upward, and the temperature and density variations associated with the wave are causing these striations in the condensation. So the imprint of the wave on the cloud is what you see. Now, by my count, there's about 25 crests across half the screen, which means that this wave is about a wavelength of about 7 kilometers or so, and periods of a few hours. This is typical for atmospheric gravity waves on the Earth. Because, as I'll get to, the restoring force is essentially buoyancy or gravity. I'll talk about them in a little more detail. So, quick outline. We can discuss these atmospheric gravity waves and their basic properties. Then talk about two sort of interesting observations of hot Jupiters, their mass loss rates, and also H2O emission has been observed and may have implications for the role of gravity waves. I'll talk about the solutions that I have obtained for gravity waves in the atmospheres of hot Jupiters in particular, that is close in giant planets, orbits on the order of 3 or 4 days. Then the implications of the presence of gravity waves, to summarize. So here's a similar image. Again, same dimensions, about 200 kilometers by 400 kilometers, taken over the Indian Ocean, the cloud deck resting about 2 kilometers up. And this time, what you see is a wave propagating away from this island. There's a volcanic island here, and as the air mass passes over it, moving in this direction, as air mass passes over that bump, essentially, it excites a wave that propagates upward and travels along with the air mass. So this is generally how gravity waves are excited on the Earth, by air masses moving over terrain, mountain ranges, and features like this. Here's another example. Again, over the Indian Ocean, a few hundred kilometers on a side. It's a little bit hard to tell with the lighting here, but there is a cloud deck here with the striations. Thanks. Characteristic of the passage of a gravity wave through this air mass. And those of you up close can maybe see that down here on the water are similar striations. What's going on here is that there is a stably stratified air mass between the surface of the ocean and this cloud deck resting at a few kilometers up. And within that stably stratified air mass, the gravity waves, presumably excited as the air mass came off the coastline over here, the gravity waves can propagate in that stably stratified slab. And so they're imprinting both on the water surface below and on the cloud deck above. From the ground, what you might see is something like this. This is a photograph taken in Siberia. And here again, the gravity wave that's causing this pattern on the clouds has a wavelength about 10 kilometers or so. So it brings me to the sort of defining characteristics of these waves. I've already mentioned that they are restored essentially by buoyancy. That is, if you take in a stably stratified fluid, you take a fluid element, displace it slightly, and the corresponding density variations cause it to oscillate around its equilibrium position. Restored by buoyancy. They're low frequency in contrast to acoustic waves. These things have periods of several hours. And because of this low frequency, they're primarily incompressible. So it's variations in density and temperature, not with pressure.
So basically what goes into that frequency, it's not such a square root of 0.
So that would be the sort of the characteristic frequency of the waves is the Brunt-Voigt-Salah frequency in the fluid, which is related. But the actual frequency of the waves that you'll excite will, of course, depend on the excitation mechanism. If you've got waves, air mass flowing over terrain, then you'll excite a whole spectrum of waves. And there's, of course, a dispersion relation that determines the frequencies of them. So what I'm going to do is sort of compare and contrast these gravity waves in different environments. First, as we know them in the Earth's atmosphere, then the role they play in the atmosphere of the sun, in the atmospheres of the outer planets, and then move on to the atmosphere of the extrasolar planets. I'll do this quickly just to sort of give you a taste of how these waves behave and how important they are in these different systems. So in the Earth's atmosphere, they're excited by terrain, and they will damp by nonlinear effects that breaking either as the amplitude grows or due to wind shear. And they do not contribute significantly to the total energy budget of the atmosphere, as the heating of the Earth's atmosphere is controlled by the sun, and the energy in these waves is not significant relative to that. So I want to contrast these 3 points in these different systems. In the outer planets, gravity waves have been observed in the atmospheres of Jupiter and Neptune during stellar occultations. So here's a profile of Jupiter's atmosphere, indicating with altitude temperature fluctuations observed during occultation. So the characteristic amplitude of these fluctuations is about 5 degrees Kelvin, and you can infer a wavelength associated with these, again, several tens of kilometers. From this data, and in more detail, from the Galileo probe, excuse me. So here, we're looking at a different region of the atmosphere, higher up. So this altitude range of a few hundred kilometers corresponds to this region down here. And here is the Galileo probe descended into the atmosphere, measured this temperature profile. The dots are data points. The solid line is sort of a mean fit to them. And what you see here is the presence of the thermosphere, is the region of the atmosphere where the temperature increases sharply. The Earth has a thermosphere as well as comparable to the solar corona. So what you see is the gravity waves that are propagating upward in the atmosphere of Jupiter imprint these temperature perturbations, and then at a high enough altitude that their amplitude grows large and they break by nonlinear processes, they begin depositing their energy. And this increase in the temperature in Jupiter's atmosphere is due to deposition of energy by breaking gravity waves. So once again, here's the variation in temperature around this mean curve, and you can infer a spectrum of gravity waves from this. And from the temperature increase, you can determine the total energy carried by them. And it turns out that the flux in gravity waves propagating in Jupiter's atmosphere is about 100 times the flux in the extreme ultraviolet that Jupiter is receiving from the sun. So although both the Earth and Jupiter have this thermosphere at several hundred kilometers above the surface, they're controlled by two totally different sets of physics. In the Earth, it's absorption of solar UV that's causing the heating. Here, it's breaking of gravity waves.
These waves, these are compatible waves now, or still? How do you get incompatible waves going vertically?
So, as I said, in the Earth's atmosphere, the waves are excited by passing over terrain. Instead here, they're excited not by terrain, but by convective plumes. So at sort of the surface of the convective interior of the planet, the overshoot of the plumes will excite these waves. Now the so no the they're very peculiar. They have so let's say if I have a wave with largely horizontal displacements, so you've got a wave vector vertical like this, then the group velocity, because of the dispersion relation here, the group velocity is actually perpendicular to the wave vector. So they sort of propagate in a counterintuitive fashion. So here you've got a wave that's propagating at some angle to the vertical. So you've got sort of somewhat vertical displacements, the wave vector like that, and they're sort of propagating upward in this way. Now, the actual direction in which they propagate will be related to their frequency. That is, the higher frequency modes are largely vertical and propagate vertically, but low frequency modes are largely horizontal and propagate horizontally. So when we come to these extrasolar planets, where these waves are being excited by the tidal potential, which is a period of a few days, it's a very long period, so they're largely horizontal modes that propagate horizontally. So in the atmospheres of the giant planets in the solar system, they're excited instead by these convective overshoot rather than terrain. Again, they damp by nonlinear effects as their amplitude grows, or wind shear breaks them at altitude. But as opposed to the Earth's atmosphere, here they totally dominate the heat budget. So as for the sun, of course, the characteristic non-radial oscillations of the sun that we're all familiar with, the P modes and the G modes. The high order G modes are gravity waves. These are able to propagate in the radiative, stably stratified interior of the sun. P modes propagate in the unstable convective envelope. Of course, the situation is reversed in a massive star. Now, the G modes have been observed in white dwarfs, which don't have a radiative envelope, so the G modes extend all the way to the surface, but they're damped out strongly in that surface layer in the sun, and are not yet observed, although claims pop up very regularly. What I want to focus on here is actually the gravity waves that can be excited in the atmosphere of the sun above the surface of the convective zone. So once again, like in the giant planets, convective plumes overshoot will excite gravity waves that propagate up into the chromosphere, into the corona. Or rather, they would propagate up into the corona if they weren't damped out, not by nonlinear effects, but by radiative damping. So in the sun, due to the high temperatures, it's actually radiative losses that totally wipe out these waves within the first 1,000 kilometers or so above the surface of the convective zone. And here, again, they contribute negligibly to the heat budget of the atmosphere.
Question.
Yes?
Technically, you described them with hypothetical equations for fluctuations
Mm-hmm.
with gravity.
Yes?
Looking for static solutions.
So now when we move on to the case of these short period extrasolar planets, the so-called hot Jupiters, with orbital periods of a few days, surface temperatures, at least on the day side, they're of 1,000, several thousand Kelvin. Here instead, you will get a significant excitation of gravity waves, not by convective overshoot, but by the tidal potential itself, if the planet is on a slightly eccentric orbit, or if its rotation rate is not synchronized with its orbital rate. In either of those cases, then the planet will experience a time-dependent tidal potential that will excite a wave-like response in the fluid. So you get the tide is exciting a train of gravity waves. Here they will damp by a combination of radiative losses, as in the sun, and by nonlinear braking, as in the Earth and the giant planets. And what hasn't been appreciated thus far is that these gravity waves may dominate the atmospheric heating when tides are strong. So either when the planets are very young and migrating in towards their parent star, during the first 10 to the 8 years, during the first 10 to 7 years of its life, the eccentricity ought to damp out. So the planet sort of circularizes, the orbit circularizes on about 10 to 7 years. Other way around. It'll synchronize first on about 10 to 7 years, then circularize about 10 to 8 years. So during that period, early in the life of the planet, that will experience the strong tidal potential that will be exciting gravity waves that may propagate upward into the atmosphere and dominate the heat budget there. Also, later on in the planet's life, so you may say, okay, we haven't detected any planets that young, so will any of this be observable? There are a handful of extrasolar planets, transiting planets, observed with measurable non-zero eccentricities. So if you believe that they're co-evolved with their host and are several billion years old, then you say, okay, well, how does it still have this residual eccentricity? It should have damped out by this time. If you have a third body in the system, it may continually excite the eccentricity of the planet. So these gravity waves would be interesting in cases where you have a planet on a short period orbit with a third body that's continually exciting its eccentricity. So you have this ongoing tidal dissipation in the form of these waves.
Is there any planet which is convincingly so? That it has this interest, it shouldn't be damped down should have been damped down the scooter?
So for all of the transiting planets that we've known, none of them has a detected second planet yet.
Well, I mean, has there any convincing examples of eccentricity driving by another perturber?
No, not for the.
Well, I know you don't have to see this other perturber.
Mhm.
I thought all the ones that have eccentric orbits actually have too long circularization time scale anyway.
So for many of them, so there are 35 transiting planets, and for at least 30 of them, the eccentricities are consistent with zero. There's a handful, about 6 or so, that may have non-zero eccentricity.
But they also have longer circularization time scale. Anyway, we can talk about this later.
In any case, they're eccentric, which is probably the most important part for your story.
Sure.
Right. So this will have implications for the mass loss in the planetary wind as these waves, as the dissipation of these waves heats the upper atmosphere, and also for an issue that I think I'll skip today, or maybe come to at the end if we have some time. This question of the thermal inversion layer. So to bring you up to date, as of this morning, there are 271 known extrasolar planets. One popped up today, 271. 35 of them transit their star. So I indicated here, thrown up the 35 transiting cases, their mass versus their period, and indicated the ones that have reported non-zero eccentricities, and I haven't put error bars on these. So it should be taken as suggestive in a few of the cases and very questionable in some of the cases. But so these three, so the ones with largest eccentricity also are on longer orbits, 20 days or so. But in that group down in the lower right or lower left, you have 4 more cases with eccentricities that may be on the order of 0.1. Here's the most famous of the transiting planets, HG 209458b. I think most people would say that its eccentricity is consistent with 0, but you can't rule out an eccentricity on the order of 0.01 to 95% confidence. So it may well have an eccentricity on that level. So it's these cases, whether there's an initial body in the system, or whether the circularization timescale happens to be long for that system, it appears as though they do have, at this time, some non-zero eccentricity. So they will be experiencing this tide and have a flux of gravity waves. This will be interesting because in 2003, an extended halo of escaping neutral hydrogen was detected around HG 209458b. So it's inferred that you've got this cloud of hydrogen extending beyond the Roche lobe of the planet that is escaping. This is a form of planetary wind. And from the observations, a minimum mass loss rate of about 10 to 10 grams per second was inferred.
How does the comparison of FUV versus gravity waves play out?
Right. So I'll show you a figure indicating that in a moment. So we'll be interested to determine whether the gravity waves can compete, of course, with the extreme UV in driving a wind at this level. And again, I'll come to the spectra issue at the end if there's time. So here's a quick cartoon of the profile of hot Jupiter. There's altitude versus temperature. May have a heavy element core. 95% of the mass is in this convective envelope. And here at this nominal photospheric level is the atmosphere. So if the infrared photosphere, there's the photosphere to the outgoing infrared flux here at about a bar, then at about 10 to the minus 9 bars is where the thermosphere picks up. So if this planet has a slight non-zero eccentricity or its orbit is slightly asynchronous with its rotation rate, then it will be experiencing the tide that excites a train of gravity waves here at this interface that will then propagate to higher altitudes, damping by radiative processes along the way, and eventually breaking due to the amplitude growth. So in addition, you've got the incoming insolation from the star. So the question is, if you're exciting some flux of gravity waves at this level, how much of that energy can you propagate up to high altitudes? That is, how much of it will damp due to radiative processes near the photosphere? So how much you're going to excite here to begin with, how much can you get up to the thermosphere, and once you do, is there enough left over to compete with the UV? So here is the figure you requested. For these 6 planets with measured eccentricities. Here's the luminosity in gravity waves that you would infer based on a tidal dissipation model of Ogilvy and Lin from 2004 versus the received extreme UV luminosity. So for 3 of the cases, it seems that if their eccentricities are as reported, the luminosity in gravity waves is in excess of the UV. The famous case, H229-458b, the 2 contributions seem to be comparable. And for these 2 cases, they're almost certainly dominated by the extreme UV. So to put some numbers to it, for a model for H229, if the orbit were asynchronous, which it probably isn't, you'd be exciting about 10 to 30 ergs per second in gravity waves. If the orbit is slightly eccentric, then you're saying 10 to 28 times the eccentricity squared ergs per second.
Asynchronous is for totally asynchronous, or is there also there must be amount of asynchronicity in there?
If it's at least slightly asynchronous, it doesn't depend strongly. It doesn't depend strongly on the difference.
It's a bit odd that
Actually, I think the number that I quote there is assuming that the planet had an initial rotation period of 10 hours, like Jupiter. Yeah.
So why does 209-458b marginal? That actually had the smallest eccentricity of any of the
Right. So
larger rays.
these 2 contributions, flux and gravity waves scale strongly with the semi-major axis and with the radius of the planet. And issue 205-498b is believed to be inflated, so it has a particularly large radius.
Why did you say that the gravity waves would be excited at the boundary of the convective layer in this case?
Right. So when you expose the fluid to this time-dependent tidal potential, it's going to excite the waves at the altitude where the natural frequency resonates with the driving frequency, which is the orbital period, a few days. So the natural frequency of the waves so the atmosphere is stably stratified, but this in the convective interior, so the characteristic frequency is the brunt. The brunt frequency goes to 0, and the brunt is larger up here. So as you approach the convective zone, the brunt goes through 0. So for arbitrarily small frequencies, you can excite waves at this level. It's about a tenth of the scale. How about half the scale height of? No, actually, they're very long. The wavelength is. So as I said before, it's the very low frequency modes are largely horizontal. So their horizontal wavelength can actually be a fraction of the radius of the planet. So they're marginally global modes. So this if you're exciting it by the lowest order tidal, the tidal component is the L equal 2 mode. That's right. Right. So it varies. But in the models that I'll be considering as an initial look at this problem, treating the atmosphere between the base of the radiative zone and the base of the thermosphere as isothermal. So the brunt will be constant.
So where you excited, what is the inversion?
So let's see. Okay. So the ratio between the vertical wavelength and the horizontal wavelength goes like the brunt over the frequency of the wave, which is about a factor of 100. So it'll be like 100th of the radius of the planet. Would be the vertical wavelength. Okay, so to the meat of the calculations I'm presenting, I've taken a one-dimensional simplified model of the atmosphere, taken linearized fluid equations with the tidal potential, separated out the quasi-static equilibrium tide, that is the familiar tide of Darwin, is the prolate distortion of the planet as a whole, separated out from the wave-like dynamical tide, which is the gravity waves we're interested in. Local WKB approximation and these low-frequency incompressible approximations to filter out acoustic modes, et cetera. Utilize opacity tables for the purpose of doing radiative transfer from Franz Allard. And I want to talk about how the radiative damping is parameterized, because this is the major question: how strong is the radiative damping as these waves propagate? That's parameterized by the thermal time scale, which is the characteristic time for temperature fluctuation to dissipate by radiative processes. So I've written down the equation governing these modes just to show you that one can separate out the equilibrium tide on the right here from the dynamical tide on the left. Of course, we have, I keep calling them gravity waves, but they're really sort of mixed inertial gravity waves because the Coriolis force is important as well. So you have the Coriolis term. This is the brunt vice versa. This is the gravity wave part. Here's the dissipation component with this radiative time scale here. And from this, you find a dispersion relation. What I want to point out here is that, again, in the dispersion relation, here's the Coriolis part, here's the gravity wave part, here's the dissipative part. As the radiative time scale goes to 0, that is when radiative damping is very effective, then this term blows up, and to satisfy the dispersion relation, you basically have to satisfy just this part. That is, what you get when radiative damping is strong is that you get a conversion from a mixed inertial gravity wave to a pure inertial wave. And that's a technical point, but I think it hasn't been appreciated in the literature thus far. So this damping time scale. It's easy to compute in either the optically thick regime or the optically thin regime. When you're optically thick, this time scale goes like the density cubed or the density squared. In the optically thin regime, it's independent of the density, so this time scale approaches a constant at high altitudes. However, what's important is the transition region, which is near the photosphere, where we expect most of the damping to take place as this time scale goes from very large to very small. When the time scale is of order the orbital period, is the wave period, then that's when you get this significant damping. So one has to treat the transition region. I do so under two approximations. First, treating the atmosphere as an infinite homogeneous medium, in which case there's actually an analytic solution to the spatial part of the radiative transfer integral. You still have to do the frequency integral, frequency by frequency. More correctly is to treat it as a plane parallel isothermal atmosphere, and I've been able to show that this approximation is good enough for the purposes, at least, well, certainly for the purposes of this talk today. Okay, now the nonlinear damping. At high altitudes, as the wave steepens, eventually, due to Rayleigh-Taylor instability, it'll overturn, and the waves will begin to dissipate. From observations of gravity waves on the Earth, it's known that the way the breaking occurs tends to be that the waves will saturate. That is, when, their amplitude growth rate will equal the dissipation rate. So they'll continue to propagate upward, depositing their energy with a sort of constant amplitude to wavelength ratio. So that's how I've treated the nonlinear breaking. The major uncertainty in all this business is instability due to wind shear. In this photograph here, what you've got is an air mass passing over this mountain, and once again, as it moves over the terrain, it excites a gravity wave that's propagating upward into this cloud bank. But then, because the wind is got wind shear, I think the wind is moving faster down here than up here. You get this characteristic Kelvin-Helmholtz instability. So the waves being excited and almost immediately damping in this case. So because the the sort of airspeed profiles of these giant planets are not well known, that's the major uncertainty, whether or not wind shear is going to kill off these waves at much lower altitudes than they might otherwise propagate to. And I can't speak to that today. Not necessarily, because you may have very strong winds on these planets. Remember that these planets are probably synchronized, so they have a permanent day side and night side, which maybe have a temperature difference, of several hundred Kelvin. So you're going to be driving strong day-night winds, strong circulation around the planet, and that the shear with altitude can be several 100 meters per second, perhaps. So it can be very strong. Right. So that's related to the issue that I've sort of skipped over, is the issue of the thermal inversion layer, that I'll talk about at the end if there's time, but please ask me again later, because I want to get to the actual damping profiles. So here's an example of a model built for HT209-458b, where the luminosity and gravity waves 10 to the 28 ergs per second, and in stream UV that it's receiving about 10 to the 24. So here is altitude horizontally going outwards, and vertically I've plotted three dimensionless quantities. So this is just a dimensionless number on the vertical. First of all, the product of the wave frequency and the radiative time scale is this blue line. So you see in the optically thick regime at low altitudes, the time scale is very long, and it approaches a constant in the optically thin regime. Here in black is the vertical amplitude of the waves and the vertical wavelength. This product indicates this is sort of a measure of the nonlinearity of the mode. And for purposes here, I say that when the vertical amplitude is comparable to the vertical wavelength, then they would be Rayleigh-Taylor unstable. So at this point, the waves saturate and break nonlinearly, as I described. And then ultimately, what I'm interested in is here, this quantity in red, the initial luminosity in waves, or the luminosity in waves over the initial luminosity. So the waves are adiabatic in the optically thick regime, and they begin damping as you pass through the photosphere at about a bar. And then once they become nonlinear, damp sharply. So the three line types are for three different assumed values of the eccentricity. It's believed that this 0.01, these dashed lines, may be relevant to HT209-458. So what you take away from here is that the radiative damping prior to hitting the nonlinear regime is relatively modest, a factor of 100. So if you've got, if the eccentricity is 0.01, then you've initially got 10 to the 24 ergs per second versus 10 to the 24 ergs per second. You lose about a factor of 100 of this, and you get 10 to the 22 versus 10 to the 24, as you get up here. So okay, for this, we saw initially that HDO29 was sort of marginal, but we should look more carefully at exactly how that energy is being deposited when it does damp. I'll skip that point. So here is a model of the upper atmosphere of the thermosphere for HDO29 from Yella, 2004, where he has modeled the heating rate of the atmosphere due to the incoming UV, and finds that at this altitude, at the base of the thermosphere here, the stellar UV is heating at about a few times 10 to the minus 7 ergs per cubic centimeter per second. I find that from the damping dissipation of the gravity waves, here again, altitude versus the dissipation rate per unit volume, once the waves saturate at this altitude, which Yella claims is the altitude at the base of the thermosphere where the heating from the UV is strongest, you get a comparable energy deposition rate per unit volume. So although you lose, a fraction of the initial luminosity is lost due to radiative effects as it propagates upward, once they begin damping, the dissipation rate per unit volume is still comparable. So to show that a little more clearly here, I've just divided by the density to have the energy deposition rate per unit mass, to sort of show that, again, the saturation here, that once the waves become nonlinear, they're depositing equal quantities of energy per unit mass as they continue upward until all their energy is spent. So what's more is that if, say, the eccentricity were larger than we believe, and you look at this line here, you start depositing energy at a rate comparable to that to UV, but at a lower altitude, meaning that you may be able, the damping of these gravity waves may be able to lift more mass into the planetary wind if you're depositing the same energy, but at a lower altitude where the atmosphere is thicker. So this will be an important input. The next obvious stage is to take your model of the planetary wind and just add the additional heat input as a function of altitude from the dissipation of gravity waves to make predictions for mass loss rates for currently known planets, and also ultimately, in particular, for very young planets when these damping rates will be largest, or when the tides are strongest. So, how are we on time? I think about that's good. Okay. So, I'll skip over this, and this is the issue of the thermal inversion layer. Please ask me about it if you're interested, and just conclude. So I've shown that I showed you a model for HD209, and for several other planets as well. Those results seem typical that the flux in the dynamical tide can compete with the EUV. There's this technical point about the conversion of gravity waves to inertial waves. I see. Here's why I wanted to make that point. The waves would be completely damped out if you were to ignore the Coriolis force, basically. So it's important to consider not pure gravity waves, but inertial gravity waves, so that they maybe propagate up to altitudes near the base of the thermosphere. The rate of loss is modest, factor of 100 perhaps, leaving you with enough energy to impact the thermosphere. Breaking of the waves may occur at lower altitudes, sort of lowering the base of the thermosphere, lifting more mass into the wind. And the major uncertainty, again, is the wind shear. Okay, that's it for now. Thank you.